like math. Sometimes when people are starting out in biology, for some reason they assume there is no math in biology, but then they soon find out they were wrong. One of my favorite topics that involves biology and math and is also absolutely fascinating is the Hardy-Weinberg equilibrium. It got its name from a mathematician and a physician, and it states that a population's allele and genotype frequencies are constant, unless there's some type of evolutionary force acting upon them. A reminder from our ecology videos, a population in this case is a group of organisms that are all the same species and can breed with each other and have fertile offspring. However, there can be variety among a population as they're not clones of each other, but based on Hardy-Weinberg equilibrium, the population's allele and genotype frequencies would remain constant if no evolutionary force acts upon them. If we have these frogs here, assume they are all the same species in this example, but there are some slight differences. In our simplified example, some of the frogs are lighter green and some are darker green. We're going to use a simple genotype in this example. All frogs in this population will be either big G, big G, or little g. There's also an allele frequency in our population. We're going to say here that 60%, a frequency of 0.6, of the alleles are big G. 40%, or a frequency of 0.4, of the alleles are little g. Notice the percentages add up to 100%, and the frequencies add up to 1. Now, to be in Hardy-Weinberg equilibrium, we have to have 5 assumptions. Number 1, no selection. No natural selection is acting upon these frogs. That means neither dark green nor light green will have any impact on reproductive fitness. Number 2, no mutation. Baby frogs inherit genes from their parents and there are never mutations. Number 3, no migration. Frogs can't come in, frogs can't go out. Number 4, large population. There are a lot of frogs. It turns out small populations are more vulnerable to genetic drift, by the way. See our genetic drift video. Number 5, random mating. The frogs mate without any specific choice. All of these 5 assumptions must be kept in order for Hardy-Weinberg equilibrium to happen. So, in real life, does this generally happen? No. For example, in real life, maybe in a certain environment, predators can more easily see the light green frogs, so perhaps they are eaten more and have less reproductive fitness. So if Hardy-Weinberg equilibrium is unrealistic in nature, why does the Hardy-Weinberg equilibrium matter? That's where the math comes in. The Hardy-Weinberg equilibrium gives you this baseline to compare how an evolving population could compare to one that remains constant without evolutionary forces acting upon it. And now let's explore the math. So there are 2 equations in Hardy-Weinberg equilibrium that we will focus on. We're going to start with the first one. P plus Q equals 1. In this equation, P is the dominant allele frequency in the population, and Q is the recessive allele frequency in the population. By the way, Hardy-Weinberg equilibrium doesn't mean that P has to equal Q, and the dominant allele frequency in any population doesn't have to be larger than the recessive allele frequency in a population. That's a misconception because dominant alleles aren't always the more common allele. The equation does say that the dominant allele frequency and the recessive allele frequency have to equal 1. So, in my example here, if I say 60% of the alleles are big G, 40% of the alleles are little g, 0.6 is P, and 0.4 is Q. So this equation, P plus Q equals 1, is for those allele frequencies. But what if I wanted to know the genotype frequencies? Meaning, I wanted to know the frequency of frogs that are homozygous dominant, which is big G, heterozygous, which is big G, or homozygous recessive, which is little g. Then I can use this other Hardy-Weinberg equilibrium equation, P squared plus 2PQ plus Q squared is equal to 1. So P squared is the homozygous dominant frequency, the frequency of big G in this case. 2PQ is the heterozygous frequency, so big G frequency in this case. Q squared is the homozygous recessive frequency, so little g frequency in this case. Let's plug those previous P and Q values in. P squared would then be 0.36. 2PQ would be 0.48. Q squared equals 0.16. Cool, huh?